So we're going to talk about integration in the first page of this packet. So integration is a calculus method that we use to find the exact area underneath a curved function, which seems like something that would be impossible to do, but weirdly, it is possible. So here I have a function. It's curved, right? And then under the curve function, it has this green area from 1 through 4. And I can actually calculate this green area if I know the function. We did an estimate of this in our investigation. In the estimate, what we did, we used kind of like graph paper. And we could see that if we put the graph paper behind the curve, we could just count up the blocks, and then that would give us an estimate of the area under the curve. And it turned out that that estimate was pretty good. Now we're going to do an estimate that's even better. What we're going to do is we're going to take this curved area, and then we're going to slice it up into vertical slices. So if we slice it up into vertical slices, the only thing we need to figure out is how high do we make each one of these rectangles. Okay, so there's two strategies we could use. And there's, of course, a strategy where you don't even use rectangles. You use trapezoids or something a little bit more precise. But what we're going to do first is we're going to use a rectangular estimate. So there's two ways we could do it. One is we could make the rectangle the highest height that is found within the interval of the rectangle. So like you can see that the left and the right edge, one of them is smaller than the other. We take the higher side and we make that the height of the rectangle. And if we do that, you can see that we end up with an overestimate of the actual area, because all of these rectangles are slightly bigger than the actual area, which has a curved top, right? This is called upper rectangles strategy. If we use the lower rectangle strategy, instead we take in the interval of the rectangle, we take the shortest side. So like the side that gives the least area for the rectangles. And you can see that this is always going to consistently underestimate the area. This is called the lower rectangles strategy. So the area A subscript L created by the lower rectangle strategy is always going to be less than the actual area A. Here's the actual area, right? This green region with the curved top. And the area A subscript U created by the upper rectangle strategy is always greater than the actual area A. By gradually reducing the width of the rectangles, you can see that like if we made thinner and thinner rectangles, then our estimate would get better and better, right? And then both area approximations will converge to the value of A. Around 200 BC, the Greek philosopher Archimedes calculated the exact area under the curve y equals x squared between x equals 0 and 1. Now what we're going to do is we're going to do some simple examples similar to what they might ask you to do on the exam. And I'll also show you how to automate part of this with the calculator. But the problems you're going to get on the exam would be simple enough that if you don't understand how to use the calculator to automate it, you could just do it manually and you wouldn't lose that much time. Okay? All right, so let's look at problem 1. We're going to look at the area between y equals x and the x-axis. Okay, so the x-axis, of course, is the horizontal axis here. And y equals x, of course, is a straight line which has a slope of 1. And it's perfectly diagonal, right? And then it says, it gives us two more boundaries, which is, they're saying between x equals 0 and x equals 1. So that would be 0 and x equals 1. So basically what they want is they want this area here, between 0 and 1, this triangular shape. Now, you already know how to calculate the area of a triangle, so you wouldn't actually use this method in this case, but just to give you a very simple problem which you could verify the answer to, they start with the triangle. Okay? Divide the interval into 5 strips of equal width and then estimate the area using upper rectangles and lower rectangles. So just to draw what that would look like, I'm going to cut it up into 5 equal segments with this black color. And it would look kind of like that, right? And so the locations of these black lines would be 0.2, 0.4, 0.6, and 0.8 because there's 5 sections, right? First, what I'm going to do is I'm going to draw what it would look like if we used upper rectangles. If we used upper rectangles, we would always make the rectangles as tall as the tallest point in the interval of the rectangle. So the heights here, the top height, this is obviously going to be 1, 1, right? So this height would be 1. This point here would be 0.8, 0.8, so the height would be 0.8, and so on, right? So the first one would actually be 0.2 tall, right? Okay, so now we have all the information we need to figure out the area of each one of these rectangles, right? So the first rectangle we're going to look at is this one between 0 and 0.2. The width of this rectangle is 0.2, right? Because it's from 0 to 0.2. And the height of the rectangle would also be 0.2, right? So the upper rectangle width would be 0.2 times 0.2, which would be 0.04, right? Between 0.2 and 0.4, the width would be what? It would still be 0.2, right? Because I would do 0.4 minus 0.2 to get the width, and the height would be 0.4. So if I multiplied those two together, I would get 0.08. And then the next interval, again, the width again would be 0.2, but now the height would be 0.6, right? See what I'm doing? I'm basically finding the area of each one of these little rectangles by first writing down the width and then writing down the height. And the last one would be 0.2 times 1, which would be 0.2. So if I added up 0.04, 0.08, 0.12, 0.16, and 0.2, that would be my estimate of the entire triangle using upper rectangles. If I use lower rectangles, the widths would always be 0.2 also, right? 0 to 0.2, 0.2 to 0.4, 0.4 to 0.6. It's always 0.2, right? The heights would be smaller, right? I'm going to draw a new XY axis here. Okay, and then I'm going to use black for the lower rectangles. First, I'm going to cut this into 5 strips. And remember that when I'm using lower rectangles, what I'm going to do is I'm going to draw the rectangle as using the smallest, the least tall point in the interval. So this rectangle here is going to be 0.2 wide because each one of these intervals is 0.2 wide, and it's going to be 0 high, right? Because the shortest point, the shortest y coordinate in this interval is 0. And the next one is going to be 0.2, and the last one is going to be 0.8, right? So it'll be 0.2, 0.4, 0.6, and 0.8. So the first area for here is going to be 0, and the next one's going to be 0.04, and the next one's going to be 0.08. Next one's going to be 0.12, and the last one's going to be 0.16. Okay, so I could just add all those up. I'm just going to show you so that you can learn something about your calculator, how you would do it using the sigma function on the calculator. So what you're going to do is you're going to use the pattern that you see here for the widths and the lengths. Okay, so let's see how we're going to do the upper rectangles. We're going to use the sigma notation, which is basically saying sum up everything that is in these left boxes. So you're going to sum up 5 numbers, which are 0.04, 0.08, 0.12. How are we going to generate the numbers? We're going to generate it using this pattern. The left number is always the same, so we could just put, okay, we're always going to have a left number of 0.2. The right number is going to jump from 0.2 to 1 by steps of 0.2. Now the calculator is kind of dumb, so the only thing it can count by is ones. So what I'm going to do is I'm going to count from 1 to 5 because we know that there's going to be 5 elements, right? 5 rectangles that we need to add up. And then we just need to figure out, okay, what do I need to multiply times numbers 1, 2, 3, 4, 5 in order to get the second number, which is 0.2, 0.4, 0.6, 0.8, and 1. Well, to multiply 1 times something to get 0.2, we can easily see that that's multiplying by 0.2. So what we're going to do is we're going to say, okay, what I'm going to do is I'm going to multiply 0.2 times k, and that will generate the sequence 0.2, 0.4, and 0.6. Let's test it out. If I put 1 in here, I would get 0.2 times 1, which is 0.2. If I put 2 in here, I would get 0.2 times 2, which is 0.4. If I put 3 in here, I would get 0.2 times 3, which is 0.6. So it works, right? Okay, so this is kind of the challenging part of the sigma notation, and maybe some people have difficulty with this. Don't worry about it. You could just add it up by hand by creating these 5 elements here. Okay? So with the calculator, we would say, okay, the sigma adding up the first to the 5th element, and the left element is always going to be 0.2, and the right element is always going to be 0.2 times the k value. And if I program this into the calculator, it's going to give me that answer. So let's try that. So I'm going to put in sigma, which I can find by doing math, and then going down here to the bottom, option 0. And then I'm going to put k. K is a popular counter to be used here. You could use other things like x or whatever. So I do alpha k, and then I put 1 through 5 because there's 5 elements. And inside the parentheses, I'm going to have to put extra parentheses because there's always like an automatic parentheses that goes around everything, these red parentheses here. So I need to put an extra set of parentheses for my black parentheses here too. So I'll put parentheses 0.2, and then I'll put parentheses 0.2 and then alpha k. And then I'll close the parentheses. And then the last parentheses is the last red parentheses. I hit enter, and my answer is 0.6. And if I look at the numbers that I have here and I add them up, I can see that they would add up to 0.6. So the answer is indeed 0.6. So the estimate using upper rectangles of this triangular area is 0.6. What if I did lower rectangles? What would be the result then? So the sigma is going to be very similar because, again, we have 5 elements, and the width is 0.2 again. But in this case, you can see that, like, if I count from 1 through 5, then I think that in this case, instead of counting from 1 through 5, what I'm going to do is count from 0 through 4. If I count from 0 through 4, then I can keep the same equation, 0.2 times k, right? So now, in order to get the first number, I do 0 times 0.2, which gives me 0, and it works, right? The last number would be 4 inserted here, so it would be 0.2 times 4, which is 0.8. Perfect, okay? So I can keep the exact same equation. The only thing I changed was, instead of going from 1 through 5, I'm going to go from 0 through 4, okay? So let me try that. Again, remember, this part with the calculator is, you know, if you like to have fun with the calculator, learn about the calculator, if you like programming. If you don't, then this part, you can follow along, but you don't need to know how to do it. Okay, and so in that case, I get 0.4. So if I do, if I add up these numbers here, I get 0.4, and you can see that if you did that in your head, you would see that you indeed get 0.4. So we know actually that this blue triangle is actually going to be between 0.4 and 0.6, because 0.6 is like the, we know it's bigger. This estimate is bigger than the actual number, and 0.4 is smaller than the actual number. It turns out that the area of the blue triangle, which goes from 0, 0 to 1, 1, is 0.5, and you could probably calculate that in your head, right? Because the square between 0, 0 and 1, 1 would be area 1. The triangle would be half of that, would be 0.5, right? Okay. Now let's do something a little bit more impressive, which is we're going to do a similar calculation, but this time we're going to do it between y equals x squared, which is our friend the parabola, and from 0 to 1. Okay, so looks more like this. Okay, so this is a little bit more challenging. We're going to use rectangles to calculate a curved area, and we're going to cut it up into 10 intervals. We represent that by saying n equals 10. So there's 10 intervals here. We're going to cut it all up, and each interval is written here 0 to 0.1, 0.1 to 0.2, etc. If we do it with upper rectangles, then we're always going to use the highest point in the interval. Okay, so from 0 to 0.1, the width of each one of these intervals is 0.1, right? Because we took the interval from 0 to 1 and we divided it up into 10 intervals. So the left number is always going to be the width, which is 0.1. Okay. What about the right number? The right number for the first estimate is going to be 0.1 squared, right? Because we want the highest point in the interval from 0 to 0.1. That would be the rightmost point, which would be x squared, 0.1 squared. Okay, and then so for the second interval, it would be 0.2 squared. The third interval would be 0.3 squared, and the last interval would be 1 squared. Okay, so those would be the numbers that we would add up to find out the upper rectangle estimate. For lower rectangles, the width would also always be 0.1 because we have taken our interval from 0 to 1 and divided it up into 10 intervals. And then the heights, instead of going from 0.1 squared to 1 squared, it would start out as 0 squared because in this first interval, the smallest point is actually 0, 0. It's the lowest point. That would be the height 0, which would contribute to this first rectangle, so it wouldn't contribute any area at all. And then the next one would be 0.1, and the next one would be 0.2. I'm just going to draw a little bit more detailed of a picture so you can see those first two slices of the parabola. So if I cut the parabola up into, the first two as two slices, if I was going to do lower rectangles, you can see that like for this first interval, the first rectangle would be 0 height because the left side is height 0, right? And the second rectangle would have a height of 0.1 because or it wouldn't be 0.1, it would be 0.1 squared because this x-coordinate is 0.1, and then the height of the red curve at this point would be 0.1 squared. Okay? So that's why this is 0.1 squared here. Okay? And then, of course, the last one, instead of being 0.1 squared, it would be 0.9 squared. Okay? All right. Now, you could add all of these up by hand. Let me show you how you would do this with the sigma notation. So for this one, the sigma notation would say, okay, I'm going to do the intervals from 1 to 10 because I have 10 intervals, and I can see that it would be easier if I used 1 through 10 in this case because it starts at 0.1. The left number is always 0.1, so I'll just put 0.1 here. The right number is always going to be 0.1 k squared, right? Does this work all the time? Let's check the last number. If I put k equals 10 in here, it would be 10 times 0.1, which would be 1. Yeah, 1 squared, that works. Okay, so for upper rectangles, I would do it just like this. For lower rectangles, I would do something similar to what I did before. Instead of counting from 0.1 to 1, now it's going to count from 0 to 0.9. So it's more convenient if I do k equals 0 to 9 and kept the inside the same. Okay, so this would be the formula to do lower rectangles. So let's do upper rectangles and then we'll do lower rectangles and we'll see the difference between the two. So I go math and then I go up because sigma is almost at the end. And then I put k, alpha k, 1 through 10. And then I'm going to put extra parentheses because remember, when we do sigma, it requires an extra set of parentheses of these red parentheses on the calculator. So I'm going to put 0.1 for the width. It's always 0.1 in this case. And then I'm going to put 0.1 times k, close parentheses. And then I'm going to square. Okay, enter. So my estimate is 0.385. So that is the upper rectangle's estimate. So that's like kind of like the largest, it's like an upper bound on the estimate. Now I'm going to do lower rectangles. I'm just going to copy and paste this because I know that the only thing I need to change is I change this to 0, and then I change the top k value, the maximum k value, to 9, and then I just hit enter, and it's 0.285. So that's kind of the lower bound of it. Okay. We don't know what the real value is yet, and we can't calculate it using math that we have learned up until this point. We're going to use calculus to calculate the correct answer, but we know that the correct answer is between 0.285 and 0.385. Okay, so that's it for this part of the video.